what you can see here in front of me, it's a wave. So we know that it's a traveling wave because if we let the motion starts, then we can see that this wave here is progressing to the right. Okay, so this is a traveling wave. And now what we need to do is we have to think about how we can describe this wave in a graph on a piece of paper. Okay, what you can see here is the wave here is now progressing to the right. But if you're sketching this graph here on a piece of paper, you can't animate the graph on your paper to move. Okay, this is a computer screen. On a paper, you cannot do that. You cannot let the graph move on a piece of paper. So in this video, what we're going to discuss is how can we draw a graph to represent a traveling wave? And if we sketch this kind of graph, what are the limitations that we have for each of the kind of graph that we have? We'll be learning two different types of graph that you can sketch for progressive wave. One will be called the displacement distance time graph. One will be called the displacement distance graph. One is displacement distance graph, one is displacement time graph. So these two different graphs has different limitation and we'll try to learn about it. Okay, so before we start looking at what kind of graph can we sketch, let's try to get an equation for this graph that we are seeing here. Okay, we'll be using knowledge that we learned from previous video to determine the equation for this situation. So we know that the equation will have this form. It will be y equals to a sine omega t plus minus kx. So this is the equation that we have. So what we need to do is we need to determine the amplitude, we need to determine the angular frequency, we need to determine the wave number. These three parameters, once we determine it, we substitute it in, and we get the equation for displacement of this progressive wave over here. So let's start with the first parameter, which is the amplitude. Well, it's quite obvious that you can see from here, this is the magnitude of the maximum displacement that can be achieved, and it's 1 meter. Therefore, the amplitude is 1 meter. Next, we progress to talk about the omega, the angular frequency. The angular frequency is related to time. So what we need to do here is we need to measure the period first. You need to measure the time taken for you to complete one wave cycle. And once you obtain the time, then you can obtain your angular frequency through the equation of omega equals to 2 pi divided by period. So how do you know the period? Well, you actually need to start the animation and you need to measure the time it takes to complete one wave cycle. So let's say I have already measured it and I measure the time, the period to be 1 second. That means it takes 1 second to complete one complete wave cycle. Then what will be the omega? Let's try to calculate. 2 pi divided by the period is 1 second. Therefore, we know that the angular frequency is 2 pi radian per second. So this is our omega. Next, the third parameter is k, the wave number. To obtain the wave number, we have to know that wave number is related to space. So we have to measure the distance the distance it takes for one complete wave cycle. So the distance it takes for one complete wave cycle, it's from 0 to 2, or you can take any point from here to here, crest to crest, trough to trough. If you measure it, the distance should be 2 meter. So if you know the distance is 2 meter for the wavelength, you can substitute in lambda to be 2. Then the answer that you get for wave number, it's pi per meter. The unit for wave number is per meter or per centimeter, depending on what kind of x-axis you have. Okay, so this is pi per meter. Therefore, we know that the wave number is pi per meter. Then once you know all three parameters over here, you can substitute it into these three spots over here. Then you get y equals to 1 sine 2 pi t minus pi x. How to determine the minus? Well, if you remember from the animation just now, the wave is progressing to the right. If it's progressing to the right, it's the positive x direction. So if the wave is progressing in the positive x direction, you need negative kx. Therefore, this is negative pi x. Okay, so before I move on, I believe some of you might be curious. Why am I showing here? It's a negative sine curve. If you look at this graph here, it's showing a negative sine curve. This is the graph. This is the moment when time is equal to 0. When time is equal to 0, you can see that here it's a negative sine curve. But my equation here, it's positive sine. I'm not putting negative 1 sine. So some of you might be thinking, maybe Segan got the equation wrong. But technically, this is the correct equation. So what am I trying to tell you here is, whether it's positive or negative sign for the displacement equation, whether it's positive or negative, doesn't depend on the shape that you are seeing on the screen right now. It doesn't depend on the shape that you see for the y-axis graph at t equals 0. Many people say if t equals to 0, then you see this is a negative sine curve, then this will be negative sine. But no, that is not the case. How do you determine it, right? The correct way of determining it is take the point at the origin, which is when x is equal to 0. If you substitute x is equal to 0, then the term behind here will be 0, right? Then you are left with 1 sine 2 pi t. Okay, so this is so what we need to do now is to see whether the particle at x equals to 0 move in the negative sign fashion or a positive sign fashion. If the particle at x equals to 0 move in a positive sign fashion, then you will move up first, then move down, then move up. This is a positive sign kind of movement. If it's moving in the negative sign fashion, then it will be moving down first, then moving upwards, then moving down. Okay, so if you get it moved up first, then it's a positive sign for this equation. If it's moving down first, then it's a negative sign. So we can check whether the particle at the origin here move up or move down. Then we can see whether we should put positive sign or negative sign here. Again, we are looking at x equals 0 because you substitute here 0, then we can remove this component. Then we focus on the shape of the graph here. Okay, not focus on the shape of the graph, we focus on the motion of the particle at x equals 0. Okay, so let's try to start the animation again, and let's try to observe whether the particle at the origin here move up or move down. Okay, so look at the origin here. So it moves up, then it moves down, then it moves up. Okay, so this is what the graph looks like. This is what the motion of the particle at x equals to 0 looks like. It starts by moving upwards, then downwards, then upwards. So if up, down, up, this is a positive sine curve. That's why this graph here is a positive sign. Okay, because if you substitute x equals to 0 here, then you're left with 1 sine 2 pi t. 1 sine 2 pi t here is the motion of the particle at x equals to 0. So you see here it's following a positive sine curve. Therefore, here you should put positive 1 sine 2 pi t. Okay, but now let's say the graph here, this wave here, it's moving to the left. If this wave here is moving to the left, then this negative sign here should be changed to positive because it's moving in the negative x direction. Then you need positive kx. So here we change to positive if the graph is moving to the left. And now let's try to imagine how will the particle move if the wave is traveling to the left. If the wave is traveling to the left, you should expect it should go downwards first. Imagine this whole curve is moving to the left, then you trace out the path of the particle, will be going down first, then after you come up, then you come down. Okay, imagine this curve over here is shifting over there. If shifting to the left. So if it's shifting to the left, you follow a red line, you will see that it goes down first, comes up, then comes down. So this is a negative sine curve because it's go down first, up, then down. If it's a negative sign, then here you need to introduce a negative sign in front. So it'd be negative 1 sine 2 pi t plus pi x if the graph is moving to the left. But now the graph is moving to the right, and we check that it's a positive sign. The particle at origin is moving in a positive sign way. So therefore here is positive 1 sine 2 pi t minus pi x. Again, this minus is because the graph is moving to the right. This plus here is because the particle at the origin here will follow a positive sign fashion of moving when the wave traveling to the right. Okay, so that's how we determine the sign in front of the sign. Okay, but if you're unsure, right, based on what I observe, I'm not extremely sure, but based on what I observe, many books or many questions just look at this shape over here. Then they say this is negative sign, then they put negative in front. Many answer looks like this. It's wrong, but I think it just happens to be like that. Okay. But if you do it properly, you should look at the particle at the origin, see how it moves when the time starts. Okay, so that's all for the equation. Let's don't go too far about it. So now we will try to sketch the graph on a piece of paper. We know that this is an animation. You can't animate something on a piece of paper. You're sketching one graph. You are not sketching an animating graph, so you only can sketch the graph with some limitation. So there are two types of graph that we can sketch, and the two types of graph, one of them is called the displacement distance graph, which is displacement y, distance x graph. So yx graph. The second one, let's go to the second one. Let's focus on the first one over here. So the displacement distance graph is actually similar to what you are seeing on top over here. This graph here is actually a displacement distance graph because this is y, this is x. Okay, but what is the limitation when we are drawing this graph over here is that we have to limit ourselves to a specific moment only. You can only draw this graph at a specific time. As you can see here, this is what we can draw on a piece of paper if we don't start the play button. Okay, it's freeze. What does it mean if it's freeze? That means it's frozen at one specific moment. So this is a displacement distance graph at time equals to 0. So the specific time that we have here is time equals to 0. This is the graph. As time passes, then the graph will move. Then of course, different time, you get different displacement distance graph. Okay, so if you want a specific time, let's try to give an example here by saying that we want the displacement distance graph when time is equal to 2 seconds. So if we want the displacement time distance graph when time is equal to 2 seconds, what we do is we substitute the time into the equation over here. So what you substitute 2 to replace the t over here, then the equation that you should obtain is y equals to negative 1 sine pi x minus 4 pi. I have taken out the negative sign out. So here there's negative. So if I take out the negative sign, then it becomes positive. Then I change the position. I bring the 4 pi to the back. 4 pi previously was positive, but because I take out the negative sign, it becomes negative. Okay, so y is equals to negative 1 sine pi x minus 4 pi. So now if I want to sketch this graph over here, well, there's a video where I explain in greater detail. Roughly, if you want to plot this graph over here, what we need to do is, okay, first prepare the axis first, and look at the shape of the graph. When you are trying to sketch this graph, look at the shape, it's a negative sign. So if it's a negative sign, then you sketch a negative sign curve first. Okay, then we know that the amplitude is 1, therefore we can say that the y is 1 over here, it's negative 1 over here. Okay, we are clear with this, we are clear with this. Next, you look at x over here. In front of x, this pi here is representing k, because in front of x is always k. So pi here is actually k. So if we know this k is equals to pi, then we can determine the wavelength. And once we can determine the wavelength, we can label the wavelength here. So how do we determine the wavelength? Well, you can just take k is equals to 2 pi divided by lambda. Okay, k is equal to 2 pi divided by lambda. Then if you shift around, you can get your lambda to be equals to 2. But basically, you can obtain here as well. X, the wavelength over here is equals to 2. So you can label here 2, label here 4. So once you have done that, you have done with this part. Then the last part that you have over here is the negative 4 pi. So 4 pi here is a constant. So it's actually a phase constant actually. So once you substitute in your time 2 over here, then this term over here has become a phase constant. So this phase constant here has a negative sign in front. That means you are going to shift our graph in the positive x direction. So that means this graph that we have drawn here, we need to shift it to the right. By how much? By the phase of 4 pi. we know that 2 pi is equivalent to 1 complete wave cycle. So 4 pi is equivalent to 2 complete wave cycle. That means we need to shift this graph to the right by 2 complete wave cycle. So how do we do that? Let's observe. Look at this point over here. We want to shift it by 2 wave cycle. So that means you have to move to here, then move to here. Okay, so I'm going to do it right now. I extend my line over here, then I shift it to the right. So I shift it. So this is 1 cycle done, 2nd cycle done. So I have shifted it by 2 cycle. And what do you notice? It's exactly the same as what I have before this. This is before I shift. This is after I shift. You can see that the shape of the graph is still the same, because if you shift your graph by multiples of 2 pi, that means you are shifting your graph in complete wave cycle. If you shift your graph by 1 complete wave cycle, you get back to the same shape. You shift by another 1 more complete cycle, then you come back to the same shape as well. So that's why the graph looks the same as if it has never shifted. Okay, but if your phase at the back is 3 pi, or it's pi over 2, or pi over 4, or pi over 6, then you have to do your shifting accordingly. That one we will discuss it in another video where we discuss examples. Okay, so why does this graph looks the same as this graph over here? It's a negative sign, then it has 1, 1, 2. It's the same graph as you can see here. Why is it so? Because if you remember, this we are asking for the displacement distance graph at time is equals to 2 seconds. So we know that the period here is 1 second. So what happened here when t is equals to 2 is you have undergo 2 times period already. So the time taken, the time that has passed is 2 period. So 2 period means by your wave has progressed by 2 complete wave cycle. So 1 period passed, you have progressed by 1 complete wave cycle. Another period has passed, you move for the 2nd complete wave cycle. That's why you shift your graph to the right by 4 pi. Because t equals to 2 here means you have undergo 2 times the period. That means your graph has been shifted by 2 times the wavelength. That's why you shift your graph by 2 complete wave cycle. So everything here connects with each other. Okay, so from here we can see that this is the graph that represents the wave at t is equals to 2 seconds. Okay, another way of thinking about displacement distance graph is to think about it as a picture of the sinusoidal wave taken at the specific moment. Why do I say a picture? Because when you're taking a picture, you are only capturing what you see at the specific moment. Okay, you are not taking a video, you are taking a picture. So if it's a picture, it's a specific moment. So this graph that you see here represents how the wave will look like. This is a picture of the sinusoidal wave. So if the wave is happening in front of you and you take a picture at t equals to 2 seconds, this is the shape that you observe. Okay, so this is what you can think about when we talk about displacement distance graph, y-axis graph. So this is the first type of graph. Let's move on to the second type of graph, which is the displacement time graph. For when you're drawing displacement time graph, the limitation that you need to accept is that you can only draw it at a specific position x. When I say we specify the position x, that means we have to specify which particle along the x-axis that we want to study. So let's say if we say x is equal to 2 meter, that means we are focusing only at the particle at x equals to 2 meter, which is here. We are only focusing at what's happening to the particle at this point over here. Then if we focus on only one particle, then we know that that particle will be undergoing a simple harmonic motion, and therefore we can draw a displacement time graph. Okay, so we are sacrificing all the other particles. We only focus on one particle, and when we focus on one particle, now we can look at how the particle moves when time passes. Okay, so what we do is we substitute x equals to 2 to replace the x over here. So pi x, right, you substitute x equals to 2 inside, then you get your equation y is equals to 1 sine 2 pi t minus 2 pi. If you look at this equation here is exactly the same structure as what you learned in chapter 9 for displacement equation of SHM. In SHM, you learn that x is equals to a sine omega t plus minus phi. And this is exactly the same shape as what you have learned in chapter 9, except that you replace the x, the displacement in chapter 9 is x, the displacement in chapter 10 is y. That's the only change that you make. Okay, so this is a SHM equation for the particle that is situated at x equals to 2 meter. So now if you want to plot a graph, it's similar to what you do in chapter 9. So let's try to plot this graph again. So the graph will be a YT graph, a displacement against time graph. We see that this shape over here is a sine curve. It's not a negative sign, it's just a positive sign. So we will sketch a positive sine curve here. Next, we look at the amplitude over here. The amplitude here is 1. Therefore, this is 1 and negative 1. Next, you move on into the bracket. In the bracket, we have 2 pi t. We know 2 pi t here. This 2 pi here represents omega. So from omega, we can obtain the period through this equation. Okay. So you know the period is equals to 1. You just need to reverse calculate it. Then you get a period equals to 1. Then once you know that the period is 1, then you know that this is one complete oscillation undergone by the particle. So you can label 1 over here. Okay, remember the axis here is time. So for one complete sign that you see here is equivalent to the particle undergoing one complete oscillation. Move up, move down, then move up. One complete oscillation, the amount of time taken, it's the period. Then second oscillation, double the period. Okay, so you determine the period to label this 2 point over here. And once you have done that, now you need to look at this phase over here. If you look at this phase over here, it's negative 2 pi. Negative means by you need to shift your graph to the right. 2 pi means by you need to shift your graph to the right by one complete sine curve. Okay, you need to shift your graph to the right by one complete oscillation. So what does that mean? Well, if you extend your graph a little bit to the left, then you shift it to the right by one complete oscillation, then you can see it move like this. So this is shifting your graph by one complete oscillation to the right, and as you can see, it comes back to the same shape. Okay, so this is your graph for y equals to 1 sine 2 pi t minus 2 pi. Let's check whether this is true or not. Based on this graph over here, we know that the particle will be moving upwards, then downwards, then upwards, then downwards, then upwards. So let's check whether this is true or not for the particle at this position here. So I will start the animation, then let's keep track of the motion of the particle at x equals to 2 meter. So let's start our timer, and then we look at x equals to 2. It moves up first, then it moves down. Okay, then it moves up. Okay, so what we predict is indeed true. It indeed starts by moving upwards, then downwards, then upwards, as indicated in our displacement time graph. So this displacement time graph here is representing the SHM displacement time graph for the particle located at x equals to 2 meter. Of course, if you substitute x is equals to 8, that means if you plot the graph, displacement time graph, then that will be the SHM graph for the particle at x equals to 8 meter. Okay, so a displacement distance graph here is representing the shape of the wave, but for a particular moment. But for displacement time graph, you are not representing the shape of the wave. This shape here, it's not related to the shape of the wave. This is just showing how the particle oscillates as time passes. This graph shows you how the SHM will be like for the particle at this specific position. So both of these graph here doesn't completely describe the actual progressive wave. They all come with a little bit of limitation. Here you have, for displacement distance graph, you are forced to limit yourself to one particular moment. For displacement time graph, you are forced to specify which particle you are studying. You cannot study all the particles. Okay, so these are the two different graphs that you can draw, and in other videos, example videos, we'll be learning how to sketch the graph for a progressive wave based on the equation given or from the equation given or from the graph given, obtain the equation for displacement. Okay, so we will do that in an example.